non-proof. Here's a non-proof. This is just a plausibility argument. d dx sum n equals 0 to infinity of Cn x minus x naught to the n, right? N equals 0 to infinity of Cn, because Cn's a constant, I can pull it outside the derivative. I'm glad I made that mistake, actually, because it gave me a chance to write this. What I'm trying to say is that item 1 is not surprising if we're allowed to make the calculation I just made. But are you allowed to do that? Can you just bring a derivative inside a series like that? Sure. The answer is yes, you can. That's what the theorem says. That means that this isn't really a good proof of the theorem because that's a circular argument. The proof of this theorem is actually somewhat technical, which I'm not going to share with you today, for you have suffered enough. Some other day, perhaps. It is nevertheless the case that the theorem is true. We can differentiate term by term. We can integrate term by... Do you see this integration? What's the 0th term here? It's a what? It's a constant, right? So you wouldn't be wrong to start the sum where? You could start this sum at 1 and just lump the 0th term into the constant. It's kind of your prerogative. Do you want to start this sum at 0 or at 1? That just redefines the meaning of the constant out front. So this is the term-by-term calculus. Oh, and then, of course, you might ask, what happens to the interval of... Well, you wouldn't ask. You'd say, let's just not talk about that. But people can ask. People want to know, inquiring minds. What about the interval of convergence? What happens to the interval of convergence for point 1 and point 2? And the theorem, when you work it out, says that the interval of convergence, the open interval of convergence, stays the same. Okay, so like open interval of convergence for the derivative or the integral stays the same. However, endpoints can get altered. So but may gain or lose endpoints. As a generic comment, we tend to lose endpoints with differentiation. We tend to gain endpoints with integration, but that's not a universal truth. It's just a slogan. All right? Okay, so example. What are we? Example 4? Power series for inverse tangent. What's the power series for inverse tangent of x? You're like, well, inverse tangent of x doesn't match the thing I've been sleeping on every night. You know, it's not a over 1 minus r. It's inverse tangent of x. Let's give it a name. Let's call it f of x. F of x equals to inverse tangent of x. But with the geometric series technique, your goal is to use the geometric series. Your goal is to somehow, by some calculus manipulation, to change the function to the format a over 1 minus r, at which point we can use geometric series. How can you change this function to make it look like a over 1 minus r? Derivative. Yeah, differentiate. And df dx is 1 over 1 plus x squared, which, by the way, we just analyzed, is the sum n equals 0 to infinity minus 1 to the power n, x to the 2n. Right? That was example 4, 5, I can't remember. My numbering is off now, isn't it? This is like 6, isn't it? It's 2 today? It's at least 3 today, because I did this one, I did that one. It's 4? Oh, it's 4? Okay. We should start giving them names rather than numbers, right? Although, shouldn't people have numbers instead of names? Wouldn't that be better? Well, it will help the artificial intelligence programming, right? Because then they'll be able to unambiguously identify who you are, and so they can give you advice on how to live your life, right? We don't want to think for ourselves, right? We want artificial intelligence to tell us how to do every aspect of our everyday. Thinking for yourself is overrated. Let us continue to critically think about this difficult calculus problem. Let's see here. So the question with artificial intelligence is, what does the word artificial refer to? So df dx is this. And then, okay, great, well, we find a power series, right? So then what? How do I get back to f? How about this? I integrate. So f of x is equal to some constant plus the sum n equals to, and I'm going to go ahead and start that at 1, because honestly, folks, it's just more convenient to start it at 1. That way, the whole constant is in the big C at the start, rather than being, you know, it's just easier for us to put the constant, all the constants together into the big C. And so we got minus 1 to the n over 2n plus 1, x to the power 2n plus 1. We don't know what C is yet, right? How do we figure out what C is? Evaluating at x equals to 0, right? F of 0 is inverse tangent of 0, and that's also going to be equal to C plus the sum of zeros. So the series, when you plug in 0, it's all 0, right? Because it's like x or x cubed or x to the 5th or x to the 7th and so forth. All those are 0. What is inverse tangent of 0? Right, 0. So therefore C is equal to 0, and hence inverse tangent of x is equal to the sum n equals 0 to infinity. Excuse me, 1 to infinity, right? Can't follow my own math. N equals 1 to infinity of minus 1 to the n over 2n plus 1 x to the 2n plus 1. That is weirding me out. The initial minus here is bothering me. Have I made a mistake? Uh-huh. Oh, that is the, thank you so much. So the danger here is that is an amazing, thank you. I cannot thank you enough for this. Exactly. I have done what? This is indexed by n. So 0, n equals 0, is a constant term. That is indexed by 2n, which means that you can't just drop the 0. Because what? Dropping the 0 isn't dropping a constant term, it's dropping x. So we don't have that luxury. We have to keep it at 0. So I guess, to be safe, it's not very convenient if it leads us to errors, is it? Let's put 0 in. Almost like I planned it. Did I plan it? I don't know. It's a question, isn't it? Maybe that mistake was for your learning. Although it seems my reaction was probably genuine. I'm not that good an actor, right? It seems like I was genuinely happy when he told me that. But then again, maybe it's just that was my plan for somebody to say it. We'll never know, right? Just kidding. I'm just kidding. You guys have seen me make enough mistakes. I make mistakes. So the point is to learn from them, yes? Now, so what is that? What are the first 3 non-trivial terms in the power series for inverse tangent? Apparently, x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7. Ooh, I get to the 4th term, didn't I? This is just so much fun. I can stop. So that, my friends, is a power series which represents inverse tangent where? Yeah. Oh. Right. At least for minus 1 less than x less than 1. Now, it may or may not be that the endpoints are legit. I don't know. Without my intuition here is that the left endpoint is I think both of the endpoints are included here because I think this is essentially the alternating p equals 1 series on both endpoints, so I think it converges both. The question is, does it converge to the value of the function? Probably, I think it does. So what's the point? Yeah, go ahead. Oh, well, a student who wanted to, if I asked for the first 3 non-trivial, if I asked for the first 3 terms and I didn't put the word non-trivial, a lazier student would write 0 plus x plus 0 times x squared. First 3 terms. In the power series for inverse tangent. Non-trivial says non-zero terms, right? So if I asked for the terms to order, if I ask for the power series up to and including order 1, it's just x. If I ask for the terms up to order 7, up to including order 7, then what I've written is the answer. So I need a way to communicate to you guys when I want like a partial answer from the series. Because there are certain questions where I don't actually want you to find the full-blown power series, right? Because sometimes it's not possible because of just the quirks of the problem. Yeah.
If you know the series of 0, where's the series of zeros?
Oh, because this is like x or x cubed or x to the 5th, and if we plug in 0 into an odd power of x, it's 0. This is the 0 series when you evaluate it. It's okay. This gives us a way, say you want to make a calculator that calculates the inverse tangent of a half. If you know this, you can build this into an algorithm for the calculator to generate values for inverse tangent to arbitrary precision using the series. It allows you to trade transcendental functions, which you can't code, for polynomials, which you can code to arbitrary precision with a fair amount of ease. Yep. Anyway, I shut up. See you tomorrow. I got it.